Everyone, welcome to Module 4, Lecture 3. This is going to be our introduction to Arduino and understanding how it's used in, how we're going to be using it, and also how it can actually potentially use in the industrial robotics industry. So this is our agenda for today. This is everything we're going to be covering. We're going to be covering what a microcontroller is, how it interacts with inputs and outputs, and how we can program it using C++. There has been some recent changes that you can actually use it with Python now. There are a couple. Arduino has it's called MicroPython. It's on their website. We'll explore this a little bit, but I highly recommend for you guys most of this the examples, not just from coming from me, but also on the Arduino forums and everything, is actually going to be in C++. So that's going to be our main focus when we get into how we can write code for an Arduino. But we'll talk about that later. So again, the goal is you guys are going to understand how this programming Arduino, how Arduino fits into the robotic world, the robotic systems, how it allows us to have sensors talk back to each other and talk to actuators and tell actuators and joints what they need to do. So by the end, the goal is you hopefully will have written your first Arduino sketch, and you'll understand what's actually happening behind the scene. And understand us learning about Arduino is not just to learn how to code, but to also understand how we are bridging that gap between software and hardware. So hopefully by the end you feel pretty confident on your understanding with that. So let's just get right into it. What is a microcontroller? We've talked about this multiple times already. A microcontroller, that is the brain of the robot. It has one specific goal and it will do that goal. It is a tiny computer that's built with only one purpose for its whole entire life. But it can do that single thing in real time and do it very effectively. It reads in inputs that is being given data that's given from the sensors. It then processes that data, usually into like binary numbers, just a readable data that the Arduino can understand. And then it will send out commands based off of that data. It will look through itself basically and figure out what it needs to do, what corrections, what's its next action, what it needs to grab. Does it need to grab with more force, less force? It will send out an output. So it's only designed to do one thing, like I said. That can either be like moving a motor or just even controlling like a basic LED. Very different from our laptops. Our laptops need like this fancy operating systems and all these softwares just to do some simple task. A microcontroller isn't trying to do a super complex task. It's trying to do a repeatable task. And it's trying to do it as well as it can. So we have things like remotes. The remote just needs to input data of like, do I turn on, off, put the volume up, down, microwaves. How much time do I need to run it on? Do I turn on or off? Thermostats. What's the temperature? Do I need to heat the apartment or house up? Do I need to cool it down? It's constantly running a program on loop. So I guess I want you to think about is how many of these small devices, like we just talked about remotes, microwaves, and thermostats, how many small devices around you, if you just look around you right now, that use microcontrollers? And not your PC. Your PC doesn't use a microcontroller, like we just said. But there are many things just by probably around on your office desk or in your kitchen that you can find that use a microcontroller. That leads into your extra credit discussion post. I'm asking you guys, what do you think are some electronics that don't need a PC that can only run on a microcontroller? Again, this is extra credit. Feel free to submit an answer just to get some extra points. But we'll also talk about this in class to see what everyone has to say. So how do we use microcontrollers in robotics? How we've talked about it already, it's the decision maker for us. It's the part that's doing all the thinking for us. So we as humans don't have to think pretty much. It's taking in data from sensors. It's processing it almost instantly. And then it decides what the robot should do next. So that's the flow of input, process, output. And that output can come in the form of moving a motor, telling the motor when to stop, when to turn, or even telling an effector how much to grip. It's designed to do everything in real time and do all those decisions the moment that it receives the data, which allows it to respond immediately to different things that are happening. The microcontroller will get the data of like, hey, let's say a servo's off by 2 degrees. It will then take that in and tell the servo, you need to correct yourself by 2 degrees. So this is why we use them in robotics. They're efficient. They are low power. They don't need 20 volts to power. They're also, they're low in cost. They don't cost a crazy amount of money, and they're always reliable. It's hard for them to mess up. Usually, if they mess up, it's not really the microcontroller. It can be most of the time it's either the actuator, whatever your output system is, or your code. To be honest, that's a big one. Again, this is why robots depend on microcontrollers, because they can make their fast decisions for them, and you need a fast decision maker when you're dealing with, let's say you're dealing with car parts, with heavy parts. It needs to know, can I actually lift this? Is this gonna cause damage? An example of one is when we're looking at their Arduinos, they have their 18 megachips. This is the brain. This is like the brain of the Arduino. This is where all of its decisions and real-time control is happening. So what is the difference between a microcontroller and a microprocessor? Both of them are brains. They both, make decisions, but they actually serve very different roles. A microcontroller is like an Arduino. It's self-contained to itself. It has the processor, the memory, the input and output pins all in its one chip. You don't need to outsource it anywhere. A microprocessor is just like what we have on a laptop. It only has a CPU. It needs external components for everything else to input and output. I mean, a computer can't tell you what the temperature is in its current area. I mean, yeah, it has like a weather app, but that's data that is being given from an external cloud source, but it doesn't have a built-in thermostat for itself to tell you what the temperature is. So to kind of clarify it, is a microcontroller has a single purpose. They are compact and they're built for one dedicated task. Meanwhile, a microprocessor is just for general purpose computing. It can just do things like here and there, but it's not really meant to send out data and tell things what it needs to do. So think of it, one's built for integration, one's built for more complexity. So why are we picking Arduino? And I think I've talked about this a little bit in class. Mainly it's not to do with, just because we have a bunch of Arduinos. I mean, that is a part of it. But the main thing is that they're low cost and it's open source, it's affordable, and it's incredibly beginner friendly. There's such a huge community. Arduino has its own forum, but even like Reddit has so many posts and articles that you can read. There's just countless and countless amounts of data and information and debugging tools and tips and code examples that you can just get just by searching up Arduino. And the software honestly is pretty simple. They have their own IDE, which is really great. They have, again, their own community that supports them. It's just great for prototyping in general. So this is really key in industrial robotics, is that you always need to prototype. You can't just build something and expect it to work. You need to have some kind of prototyping that's happened. And working with Arduino, since it's so simple and since it's open source, there's so much data, it actually makes prototyping a little bit quicker. And we'll call that rapid prototyping. And I'm always going to, I always tell students, once you understand Arduino, you pretty much can easily understand other systems like a Raspberry Pi or the, I believe it's called ESP32. The name's escaping me right now, but I'm pretty sure that's what it is. They're honestly all very similar. It has inputs, outputs. It can, again, read data, send out data. It can tell what actuators need to do. They all have their own brains, their own power supplies. They're all set up the same. But we're just choosing Arduino just because it actually does. It's probably one of the biggest forums out there. So let's get a little bit more into it and understanding how we can use it. So let's look at it a little bit more in depth. We're breaking our Arduino down into 10 sections. Let's break down into each part. So part 1, we're looking at our digital pins. We use these pins to read our digital data, also write digital data, and write analog data. Keep in mind the analog write data works only on the pins that are labeled with the PWM symbol, and we'll look at those more once we physically are looking at our Arduino. And then we have our built-in LED, or we call it pin 13. It is actually it's built into the board. Pretty much Arduino built this in so you can use it as a debugging tool. This is gonna be great. This is gonna run like our first program just to make sure everyone has a very basic understanding of just a really simple code, really simple script, and also can see the LED because it's a little tricky. It is pretty small to see, but it is, once again, a really great debugging tool. If you're not sure where your code is messing up, use that LED. Tell the LED to turn on or off. You can see what step you are on in your code. And then the third part is our LED indicator. This is just telling us, hey, is my Arduino receiving power? Again, another useful part for debugging. If that green light's not on, something's going on. There's no power supply getting input into our Arduino. And then we have our ATmega microcontroller. Again, that is the heart, the brain of our robot. Our board. It's converting all of the data that we are getting from our digital and analog pins and telling what our outputs need to do. And then we have our analog read pins. This is just reading in data, for example, let's say from like an ultrasonic sensor. It's just reading what it's reading, how far distance it's saying. Is there something 30 centimeters away? How do we get that information? So that's what these pins do. And then you have your ground and voltage pins. Arduino is only capable of powering up to 5 volts, so perfect enough for an LED. It can theoretically power a motor. It would be very low powered, not super strong, but it can power a very small motor. But you can, and we're gonna be doing this in labs of actually wiring up an external power supply, like the one that we were using in the labs before, to hook it up and actually give more voltage. You can overpower an Arduino though, so you don't really want to do more than 12 volts from an external power source. And then our seventh component is going to be our power connector. This is how we connect that external power supply. Again, right here, it says anywhere between 7 to 12 volts is the recommended for an external power supply. Please do not do any more than that. Honestly, I don't even recommend jumping up to 12 volts. I would just do 10. You can burn these out. I have done it by accident before. Don't just 7 to 10 is the sweet zone. You don't need to hop up to 12. If you're hopping up to 12, I'm gonna be asking, what are you trying to power? And then we have our TX and RX LEDs. This is just telling us that our Arduino is having successful communication with our computer. Expect these to always flicker. Don't freak out. They're just letting you know, hey, I can tell you're uploading code, and I'm letting you know I am talking to the computer. This is how we'll be able to do a lot of our debugging. This is how we're going to do all of our serial communications. This is how, again, the Arduino is just a light indicator, instead of just data coming into our laptops and seeing it on the terminal console. This is its way of telling us more visually with a light is that it's, hey, I'm sending out data to you. And then the ninth part is our USB port. It also serves as a power supply for the board, but it also lets us upload our sketches to our Arduino. And this is how we communicate with our Arduino with the sketch, getting the serial data. This is how when it's printing out, that's how it's getting back. It's got to be hooked up back up to our PC or laptop, whatever you guys are using. And then 10 is just our reset button. It resets our microcontroller. I usually recommend when we get into debugging and troubleshooting, try giving the Arduino just a reset first before jumping into trying to see if your code's going wrong or if just nothing's happening. Give it a quick reset. It's not out of the question where sometimes when you upload a sketch, it can kind of freak out for a second and doesn't fully upload a sketch. So if you just give it a quick reset and re-upload it, it usually fixes itself. So kind of what is this whole entire process? This is where everything connects. Where sensors are sending out signals. So we have our input. That's our sensors. It's an ultrasonic sensor or a limit switch or a torque sensor. Plus a combination of our processing that is done by the Arduino. This is what gets us our output. This is what tells us what our actuators, what our end effectors, like our gripper or suction cup, what motion that needs to be performed. So for example, let's look at this. When we look at a distance sensor, let's see here. We'll draw a little distance sensor dude. He has his little eyes. And he is detecting an object that is like 30 centimeters away. So this is our input. All of that gets converted over to the Arduino. We'll draw our little microcontroller right here. Have our little... I'm not an artist, so we'll do our best right here. Awesome. So this is our processing. Gets moved out into our output, which we'll draw a servo. And this is just performing all of our rotations, our movements, our output. So that's pretty much what's happening. We're having a sensor data that's getting read, that's sending information back to the Arduino, and the Arduino is then telling movements, move 2 degrees right. So, what is the Arduino really reading? When we look at an Arduino, what is we need inputs. So the inputs is how the Arduino is sensing the world. We have digital inputs and analog inputs. We're gonna look at digital inputs right now, really quick. They're the most simple ones. Digital inputs are just simple on and off, high, low, true, false, 0, 1, just different ways of looking at it. For example, it's like pressing a button. When you press a button, it's either on or off. And then we have our analog inputs. This is actually giving a range. We can look at our distance sensor again. It is telling us a range of you are 31 centimeters away, 32, 33, 34, 35. It's not just a simple on or off. It is giving you a value back, like an actual numerical value back. And each of these sensors has to be connected to a specific pin on the board. You will see that when we are looking at the board. And how you figure this out is your understanding of, you have to make sure you know what type of sensor you're using and what type of data that it gives and gives back. Really quick, I forgot to mention this. The Arduino, when we're doing analog input, it is going to be on our pins. They're on the left side of the board. They are A through 5, so A 0 through 5. Analog 0 through analog 5, that is how we're receiving input. And how we receive digital inputs, it is any of our Arduino pins between 2 and 13, so D2 through D13. That is how we will get any of our digital inputs. They're yes or no, pretty much. Here's just a quick chart that I made explaining this of kind of the logic behind it. So when we're looking at a digital input, this is just simple logic. Like I said, on or off, 1 or 0, low or high, is a button pressed or not, like true, false. Really, really simple. Analog is going to be a variety of numbers. So we have like our range of 0 to 1023, any number, any voltage between 0 and 5. You can see that with a potentiometer. Those are just like a couple of, potentiometer is just one of the examples. There's so many sensors. Most of the sensors honestly are analogs. So this is just a simple chart. You're probably going to be looking back at this a couple of times when you're first looking at an Arduino. So what are outputs? Outputs are what the Arduino uses to act on the environment. Digital outputs can switch things on or off. So, hey, I just want you to turn this light off, or I want you to turn it on. And we kind of saw that when we were working with these circuit boards, when you were turning the power supply all the way off to 0 volts and turning it all the way up to 6 volts. We were seeing how we can turn a light on or off, and this is going to work the exact same once we throw an Arduino into a circuit. It's just going to be able to do on or off on that. And then our analogs, this is honestly one of the most important parts. We have PWM. This is pulse width modulation. This is a rapid fire signal of on, off, on, off, on, off. This is how we do motor control. This is how we control the speed. Motors take in this on and off spikes that are happening, and then lower the spike, the lower the speed. The higher the spikes that are happening, the higher the speed that this motor is moving. So we can use that to just control a whole bunch of different things. Again, the best example is looking at is a motor. So kind of looking at, here's like a quick little chart, an ultrasonic sensor. What kind of, is that an input or output device? It's an input device, it's an analog device because it's giving us a range of data. So we look at it, it's 3 centimeters is what it's reading right now. And we'll actually get into this a little bit more. Ultrasonic sensors have a minimum range and a maximum range. If you are below the minimum range, it actually will start to freak out and say that your object is like, I think if it's like a range of 1,023 centimeters away, which that is clearly not correct. Anywho, and then we have our digital inputs. So this is yes or no. So a simple switch. And we have our outputs. This is what is happening, what movement's happening. We have an analog output is going to be a motor. It can move at different variations of speeds. And then just a simple digital output, an LED turning on or off, just indicating that something is happening. So we're going to stop right here, actually. We're going to wrap up right here, and we're going to pick up in the next video of how do we actually program an Arduino. Awesome.